All right, so constants are really one of my most favorite things in Go, believe it or not. I learned so much about the language when I started studying constants. And every time I think about how constants work and how they've implemented them, it always freaks me out a little bit. It's really amazing. All right? So I always start off by saying that when I'm talking about something that's an implementation detail, you need to be very aware of that. Right? So the specification, that's fixed, right? So we have backwards compatibility as it relates to the spec, as it relates to the standard library. But the implementation of things can change. It happens all the time. But they've just changed how stacks work in the language from 1.2 to 1.3, right? So if we were writing code based around the implementation of stacks, a lot of our code would now be broken as we moved on. And so some of the things I'm going to be talking about are implementation details. And it's nice to know the implementation details are going to help you find bugs quickly. But we cannot be writing code against them. So constants are not variables. Right? When we declare a constant in the language, we're declaring something that exists only at compile time. Eventually, every constant that we use has to be converted to a variable. All right? That's really interesting. Primarily, as you guys probably have hit up against it quite a bit, Go is a type-safe language. So everything we do, whether it's with our variables, whether it's math, assignments, we're comparing things, you've got to have like types on both sides of those operations. Right? The compiler and Go is never going to implicitly convert a variable for you at all. Now, if our constants were variables, they would have that same exact restriction, right? Which would make the language very difficult to use. But instead, as you're going to see, constants give us that bridge to allow us to do things in a very intuitive way with values, and yet we still have a very type-safe language. I like to think that constants have a parallel type system. Right? And what's nice is when we have untyped constants in our programs, the compiler can perform those implicit conversions that can't happen with our variables. And that's where we get a lot of flexibility in the language. Those constants give us the flexibility to have implicit conversions, to work with values, and work with them intuitively. So take a look at these two constants that I've declared here. They're untyped. Keyword const. I've given it a name, and I've assigned it a value. Now, when we're dealing with untyped constants, it's really good to think of a constant as not having a type. It has a kind. So these two constants, the first one has kind integer. The second one, it's good to think of it as kind floating point. When something just has a kind, then it can be converted implicitly to a type. The compiler sees the decimal point on the second one and determines that that's going to be of kind floating point. They're both numeric, but we can make the distinction that one's an integer and one is a floating point. Now, anytime we go to now run this program and display these values, these constants have to get converted to a value, a value of some type. And so when I run this printf command, I'm really not displaying the value of a constant. I'm displaying the value that was converted from constant to now a value of a known type. But when I run this, we're going to be told that UI is of type int and UF will be of type floating point. The compiler will do that implicit conversion for us. Now, here are two constants where I've bound the constant to type information. Now, this is really important. I said that constants have their own parallel kind system. What that means is from an implementation detail, constants are not implemented the same way variables are implemented. In fact, our constants have much greater precision built into them than our variables do. The specification has some arbitrary precision. In other words, when we think of constants, we want to think of them as being mathematically exact. All right? So I can technically store an integer value of any size. If you want to type for the next 3 weeks, from a specification standpoint, we can store that number. Any floating point number, we like to think of that as mathematically exact. Now, from a specification standpoint, this is all that it says. It doesn't say how things can be implemented, but integers have to have at least 256 bits. Could there be a compiler that uses more? Absolutely. Right? But this is from the specification requirement. Same thing with floating points. The mantissa has to be at least 256 bits. We could also, from a floating point, do rational math, right? The compiler could do fractional math to be exactly precise. The idea here is, though, is that we're using so many bits to represent these numbers that they are, in essence, mathematically exact. That gives the compiler and constant arithmetic an advantage over our types. Because an integer is bound to how many bits? 64. Right? Our floating points are IEEE 754. They're bound to that precision. But our constants are not bound to any precision. That's the way we need to think of them. Though obviously at some point here, there's, in this case, at least 256 bits. So, like I said, constants kind of have their own parallel type system, right? The way an integer or a floating point or those values are stored are completely different from the way they end up being stored for our variables. So when I see these two named typed constants, all the type is doing is it's binding that value to that precision. It's not storing it as a variable would be stored. It's still using the compiler's representation parameters. There's 256 bits of precision can still be there. Okay? So these are not variables. They're still constants, but we've kind of handcuffed these constants. They're now bound to that type information. Right? So I now have a constant here of type int64. It is still a constant. It's not a variable, but now it's bound to the laws of what an int is. It's also bound to the laws of having like types on any operation that we perform. So it's really handcuffing the constant. That's the way I see it. But there are times, and we're going to see, where doing that is good. So here's a constant that I've given a type to, uint8, and I'm trying to assign the value 1000. This is going to give me a compiler error. Why? Because the constant is bound to the type information at that point. Is this a variable? No. It's still a constant and represented by the compiler as constants are, but we've handcuffed it. The compiler will not allow that to happen. This gets really interesting when we start looking at constants in math, because if I try to take two variables, if I take a variable of type int and I take a variable of type floating point, the compiler will not allow me to do math across those. I will have to convert one value to be the same type. But look what's happening here on line 36. I'm declaring a variable, right? I've used the keyword var here just to make that very clear. That answer is going to be a variable, but its value is based on the math between the literal value 3, and literal values, by the way, are constants in Go. So that 3 is what I call an unnamed constant, and times 0.333. When we have constants that are not typed, I like to think of them as kind. So I've made this up here just so as we talk, I want you to think in terms of kind. So 3 is of kind int, which means it can be converted to any numeric type that is compatible with it. .333 is of kind, and I screwed up my comment there, so I'm sorry, kind float. Now, we're doing math against something that is kind int and something that is kind float. So what is the result of that math? Well, there are rules for kind promotion in the language. In this case, float is going to be promoted over int. So this equation is going to create a constant of kind float. And then that constant of kind float, that literal value, gets converted to a value of type int. And the compiler can do that. There's an implicit conversion going on by the compiler here because we're working with kinds, constants of a kind. And as we talked about, the precision at the constant level, the constants type system has so much greater precision that doing this math has greater precision as well. But as soon as I try to, in this case it's a variable, but again, anytime I see a printf or a print line, that constant is not what's being displayed. A conversion of that constant to a value of some type is what's being displayed. So let's look at this here. And hopefully you guys can see it up there. So here is a, oh, I can always send that to you. So here is a constant that we're declaring, and it equals 1 divided by 3.0. So what is the result of this constant? This constant is going to be of kind floating point. This constant is a constant. It's not being bound to a type. So 1 divided by 3.0 will be kind int divided by kind float. Float gets promoted. And so the result will be that division as precisely, mathematically exact. That's where we want to look at it. And now constant is going to be a constant. Third is going to be a constant of kind float. What's happening here? I'm doing math against two constants of kind int. So 0 is going to be of what kind? Int, which means the value of this equation is going to be 0. There's nothing there to turn it into a floating point to get the exact representation of 1 divided by 3. So I have, in this case, a constant of kind int. And here's a case where I'm declaring a constant, and I'm giving it specifically this type information. I'm saying this constant is of type int 8. Is it still a constant? Yes. But I've handcuffed it. I've bound it to type. I've assigned it the value of 1. So this is a constant. That 1 is a constant, right? It's a constant of kind int. Yet the compiler can implicitly convert that value to a value of type int 8. Really a constant that's bound to int 8. Now look what I'm doing on the next line. I'm taking the literal value of 2 times 1. 1 is a constant, but I've bound it to type int 8. Anytime I'm dealing with type, I have to have like types on either side of that operation. So what does the compiler do? The compiler treats 2 now as an int 8. If that literal value cannot be represented as an int 8, we will get a compiler error. And so the result of this math here, 2, will end up being a constant of type int 8. Okay? Int, this type is going to get promoted at that point. So if there's a type involved, then we didn't have kind promotion here, we had type promotion. However, constant 2 is still what? Still a constant. So if I run this program, and even though it's running, every value being displayed on the screen down here ends up really not being the value that the constant had. It is the value of that constant being converted to a value of that particular type. You guys see all that? This is This is cool stuff, right? That untyped constant has a lot of freedom. I'm going to show you now an implementation from the standard library that when I was first learning Go, I'm going to show you this first, and then I'm going to show you that. So how can I prove to you that constants are mathematically exact when every time I go to run a program, constants have to get converted to a value of some type, right? When our program is running, the compiler is gone. So take a look at this. Here are two constants. The first constant represents a number that is the max integer value for 64-bit. So that's it. Look at bigger, the constant bigger. How large is the number that I'm storing in that constant? I've made it significantly larger than a 64-bit integer. All right? So if the compiler is mathematically exact, and I try to compile this, I should not get a compiler error. And I won't. I can run this program right now. Oops. What just happened there? That wasn't fun. I lost the airplay. Here we go. So I run this, it compiles and runs. Now, if I uncomment this line right here, what am I doing here with this constant? I'm binding it to type information, right? The type system that we use for values. Now if I try to run this, I'm going to have a problem. And it's not because the constant itself can't store that number. This is still a constant. It's because I've bound the constant to only that level of precision, and it will respect it. I wish I could do this for floating points, but this is the only example I can come to show you how these numbers are mathematically exact. We can store numbers larger than what our value type system can handle. This really tripped me up when I was first learning about Go, because I was looking at constants as being just read-only variables. Oops, sorry. So let's start with something here. So that is a named type in Go. I'm declaring a type, its name is duration, and its base type, it's based on an int 64. This comes from, this is how duration is actually declared in the time package. But let's look at a few things here. So there on line 12, I'm declaring a variable called duration of type duration. I'm displaying the value of duration on the screen, which will be the 0 value for that variable, so we should get 0. And then I'm declaring another variable here called nanosecond. I'm taking the literal constant 10, converting it specifically, right, explicitly, to a value of type int64. So nanosecond is a variable of type int64. The same type as duration's base type is, right? But in Go, as far as the compiler is concerned, if I try to do this assignment, I'm dealing with variables of two different types. It doesn't matter that duration is a name type that's based on int64. After that declaration, duration is duration. Its representation underneath is irrelevant. These are not compatible variables. They are two different types. And so if I try to do this, I'm going to get an error that's very specific. Cannot use nanosecond type int64 as type duration. The compiler's telling you, these are apples and oranges. Not going to happen. All right? In order to make anything like that work, I've got to explicitly convert nanosecond to a value of type duration to be able to have like types on that assignment. So Go is a type-safe language. If you want to play you've got to play with like types at all times. That keeps everything nice and safe, keeps you out of trouble. But you can see how restrictive that is, right? We have to do these conversions in order to be able to take these values and use them in different ways. But the language designers, because of constants, it's brilliant. They're going to give us back all that flexibility. They're going to make the language really simple and easy to use thanks to constants. So this is pulled right out of the time package. That's the name type duration. And here are constants that are declared in the time package. These are typed constants, right? The first constant right here is of type duration. It's set to a value of 1. And then we're doing constant arithmetic here, right? But that value 1,000 is going to be treated as a value of what type? Duration, because of type promotion, because this is also of type duration, which means that this constant is going to be of what type? Duration. Cool. So I've got all of these typed constants, right? They're all of type duration. All right, let's get to know. And then I have this function that we're going to play with. Add. Add takes a value of what type? Duration, which we know has a base type of int64. But duration is still duration, and int64 is still int64. All right, let's see how this works. So here's a constant that I'm declaring that's going to use some multiplier here. What is 5 seconds after this? Well, I'm taking the literal value of 5, which is of kind int. I'm multiplying it by time.second, which is a constant of type duration. We do that math, and 5 seconds is going to be a value of type duration. So this is a typed constant. No problem. So I get now, we use the time package, we get now, and look at this line right here. Add takes a value of type duration. What am I passing to that function? A constant of kind int. I'm passing a constant of kind int. That means that the compiler can do what for me? It can convert it to a value of type duration that is compatible. How cool is that? Same thing on the next line. Line 45. 5 seconds is a constant of what type? Well, constants of type duration can be converted to values of type duration. That is also legal. But you see how the constant here on line 42 gave us that flexibility to work with literal values? I didn't have to explicitly convert that to duration because it's an untyped constant, because it's a kind int. The compiler can step in and go, okay, I'll fix that for you. No problem. I'll let the call go through. We'll make it happen. Because it's happening at the compiler time, right? The compiler can guarantee the safetiness of that statement. How cool is that? The flexibility we're getting from that constant. So if I run this, everything will run. Now I'm in the playground, and in the playground, time is always fixed, which is always fun when I try to do things with time, and I try to randomize things on time. It never really works. But the point of running this is that it compiled. It was able to do those implicit conversions because those constants were of kind. Let's take a look at this next one. Same thing. We got our name type. We have our constants. Okay, we've got our add function. I've created my 5 seconds again. Oh wait, I just looked at this one. Oops. Sorry. No, I did that when I was running through this too. Okay, here we go. I'm just doing some bad things here. I'm creating a variable here of type int64 by explicitly converting the value -5, which is a kind integer, to an int64. So -5 is a variable. Now, I try to pass that variable of int64 through add. You might think at first, well, duration is the base type of duration is int64, so this should work. But it won't. The compiler now is going to say, no, you don't have like types. That is not a constant of some kind. That is a variable that is already bound to type. We've got to have like types. And when we look at the error that follows, it's very clear. Okay? The type is not right. So we're going to get that error. So the constants can be implicitly converted, but our variables cannot, even when we know the base type is compatible. All right. Now I've done something a little different on line 34. What have I done? I've handcuffed that constant. It is no longer going, in this case, well, I've done something even worse to it. I'm not even allowing the promotion of the math to set the type of the constant, right? I'm trying to say, hey, I want this constant to be of int64. But that can't happen because promotion is going to make all of this duration. So I'm going to get a compiler error here. At the constant level, it's going to tell me very specifically, I can't use this literal value 5 as duration times another value of type duration as int64. I really love the compiler errors that come out of Go. If you really read them, they're very descriptive of what is happening here. And first I used to scan through them. But now when I get a compiler error and I don't really know what's happening, and you look at that language, and a lot of it came to me from reading the spec over and over again, which was a chore for me. But once you learn the language in the spec, and you see these compiler errors coming through, they match very, very clearly. It's very rare an error comes out of the compiler that can't be found at the spec level. And you can understand very quickly what's happening here. But I've created two problems in this program. Even though 5 seconds doesn't compile, the compiler still sees it as type int64 because of the way I declared it. And here now, I'm trying to take a constant of type int64 and pass it through this function as type duration. The compiler says again, no, it's not going to happen. So when I work with constants, and you can see the time package is using a typed constant, right? Very, very effectively. But when you start looking at your programs and you might get these type errors, and you're working with constants, look at that constant. Is this a typed constant or an untyped constant? Do I need flexibility in this constant? If this is something that I might want to use, and I need these values, these literal values to be converted to other types, I need to use an untyped constant. And let the compiler do that work for me. Get the flexibility in the language so I can work with these literal values without having doing explicit conversions. Let the compiler do that work. There are times, though, as we saw, the time package, where it's nice to bind that constant. Why? Because when I'm doing that mathematics, I want the math to be bound to the type that I'm dealing with. And if I'm working with those constants, right, that duration, the duration value, a lot of the functions in time work with values of type what? Duration. So what I've also done is from an API standpoint, I've kind of enforced that everybody has to be working with duration, right? They've created an API around the constant. You want to use add? No problem, but we're only going to take duration. You want the greatness of constants with all that mathematical precision? No problem, right? But if you want, in this case, I have very specific values for each time. Seconds, milliseconds, they're all of a specific time. But I'm now able to just bind that to a type and use it as part of the API. So this is why I love constants. It was like, we have this type problem. I'm not going to allow these types to ever implicitly be converted. But the programmer needs flexibility. We'll do it in constants. we'll create that parallel type system, kind system. And now when they need the flexibility, they can have it. And then when that API that we're building needs to be bound to something specific to make sure that we're doing things right, we can bind that constant too. That's my talk. I always forget to ask these questions. I'll try to answer them as best as I can. Yeah.
How is it addition handled when constants are larger than 64? Like you're adding 2 and 64. You're adding 2 constants that are larger than 64. Is that how?
You absolutely can do math. All math. Yeah. So he asked me, what happens if I'm trying to do multiplication of 2 integers that are larger than int 64? The compiler is going to do it. We look at those untyped constants as mathematically exact. So you want to spend a week typing in integers, we consider from the specification that that's going to happen. But what's the problem? At some point, that constant, the value of that constant has to be converted to a value of some type. So at that point, you're going to have truncation. You're going to have that precision come out. Right? Because we can't work with constants forever. Eventually, that program has to run.
Well, would you get truncation or would you get an error?
You won't get an error.
So if at the end you say
The compiler is going to implicitly convert that value to whatever that type is. If it can't fit, there's going to be truncation.
What if you declare that constant very long in here, and then you form a percent %t, you print percent capital T for the type? What will it do?
Remember, as soon as I call printf, that constant no longer exists. It has to be converted to a value of a known type. Which is why the only way I can show you that constants are mathematically correct is by declaring an untyped constant, putting a really large integer in it, and then just seeing if the compiler fails. I can't display it. It's going to have to get truncated. You only have 64 bits for an int.
Well, you can take 2 really big integers and like subtract them and display the result of that.
If it fits inside that 64-bit,
Yeah.
then you're going to be fine. Right? You'll see it. Yeah.
Do you have any advice for statically typed enums? Say I was writing an IP library and I wanted to have IPv4 and IPv6, and I only wanted users of that library to pass one of those 2 values into a function. Can you do that as far as
Well, isn't that kind of what we just saw with the time package? They declared a named type, right? And that named type became part of the API for all those time functions.
But I can pass in a variable which is like 7, and it wouldn't be, since it's type checked to an int, it would.
The 7 can be implicitly converted. Just like today, if I put 5 in that add function, what am I really passing? I'm passing the 5 microseconds, right? That first constant. So, and remember how many people have tripped up on that? I did, right? A bunch of times. So
there's no way to do a statically typed set of enums.
a statically typed set of enums. But what is the purpose again for that?
Again, if I had IPv4 and IPv6 as named constants, and I only wanted to develop.
Let's talk after, because it's a little much. And what we see. Yeah.
Are you able to bound the domain of type conversions with custom types, or are you bounded to the limits of the actual primitive type underlying the constant?
Right. Ask that question one time. No, I wasn't sure I understood the question.
Okay. So, like, say you wanted a custom type and you only wanted to be able to have 1, 2, 3, and 4 as values, for instance. At compile time, are you able to make the assumption that nobody is trying to make a type conversion outside of the
Not that I
range
know.
of 1 to 4?
I've not seen any implementation that would support that. I haven't. Yeah.
Are we able to use any of these, assuming there's sort of a big calculation being performed in compile time, are we able to use that code at runtime and then we expose that implementation for usage at runtime? Or are we limited to using that implementation at compile time?
Those untyped constants and that math you saw is all compile time. At runtime, now we're talking about values of that other type system.
So if I
There's a package called Big. There's a Big Math package already in Go
Okay.
that will give you the ability to work with very large numbers and do rational math as well. So the support is there already. It's part of the standard library.
Side question, do you use that same implementation from Math Big to implement constant math?
I don't think so.
Interesting.
Remember, you have to, eventually your program has to run, and you have to work with values of that type system. These untyped, these constants are a compiler level construct, giving us that flexibility to work with literal values so they can be implicitly converted and make our code very easy and clean to work with. It would be a nightmare if we had to explicitly convert the number 5, let's say, to some type that we need. Good? All right, thanks.
All right, so it's